Good day, we are the fifth group and we're here to present about the chapter 9 of the FAA Helicopter Flying Handbook entitled Basic Flight Maneuvers.
Next slide, please. Next slide. So first, let's go through our overview. So we have introduction, the four fundamentals, straight and level flight, turns, normal climb, normal descent, vertical takeoff to a hovering turn, hovering forward flight, hovering sideward flight, hovering rearward flight, and last one is taxiing. Next slide, please. So why do we need to know basic flight maneuvers? Understanding basic flight maneuvers is crucial for several reasons. First and foremost, it directly impacts safety. There are various factors significantly impact the performance of a helicopter, even when flying the same model. Pilots must remain acutely aware of these variables and be ready to adapt their flying techniques accordingly. The basic flight maneuvers outlined in this chapter serves a general guide applicable to the most helicopters with caveat that specific adjustment might be required based on the prevailing conditions. Next slide, please. So there are techniques applied in small training helicopter. First one is a single main rotor. A spinning counterclockwise is a fundamental feature of many helicopters. This rotor generates lift and provides stability during flight. The main rotor is a key component responsible for lifting the helicopter off the ground. As a helicopter rotates, they create lift and pushing air downward. This upward force counteracts gravity, allowing the helicopter to ascend. The lift generated by the rotor is proportional to the angle of attack, the angle at which blade meet the oncoming air, the rotor's rotational speed. The next one is an anti-torque system. So an anti-torque system serves as a crucial role maintaining stability and controlling its yaw rotation, the rotation around the vertical axis. There are four types of anti-torque system. The first one is tail rotor. It is the most common anti-torque device. It is mounted on the helicopter's tail, and when the main rotor generates torque due to its counterclockwise rotation, the tail rotor produces sideways thrust to counteract this torque. The second one is the fenestron fan in tail. This system is an alternative to the tail rotor. It consists of a series of rotating blades enclosed within the circular duct located in the vertical tail. Next one is the no-tar or no-tail rotor. This uses aerodynamics to achieve anti-torque control. So how does it work? A variable pitch composite blade fan inside the tail boom produces a low pressure, high volume ambient air. The air exits through the slots along the tail boom, creating lift and countering torque. Last one is anti-torque drive system. An anti-torque drive system includes an anti-torque drive shaft and an anti-torque transmission mounted at the tail boom's end. The drive shaft may consist of one long shaft or a shorter shaft connected with flexible couplings. The tail rotor transmission provides right angle drive for the tail rotor and adjusts output for optimum rotor RPM. Next slide, please. Here are some guidelines for basic flight maneuvers. The first one is move the cyclic only as fast as trim, torque, and rotor speed can be maintained. The cyclic in the helicopter adjusts the pitch of the rotor blades, affecting the aircraft's movement in different directions, forward, backward, left, and right. In other words, we don't exceed the helicopter's ability to maintain stability and control during cyclic inputs. Second one is when entering a maneuvering and the trim, rotor, or torque reacts quicker than anticipated. Pilot's limitations have exceeded. During a specific maneuver, such as turn, climbs, and descent, The helicopter's trim, rotor, and torque will respond to your inputs. If this response happens rapidly than expected, it indicates that you've pushed the aircraft beyond its limit. This warning sign that you need to adjust your approach to avoid exceed safe operating parameters. Third one is if you continue, an aircraft limitation will be exceeded. Ignoring the warning sign mentioned before can lead to exceeding the helicopter's limitation. Continuing with aggressive maneuvers could result in damage to the aircraft or even loss of control. Fourth one is perform maneuver with less intensity until all aspects of the machine can be controlled. So if you encountered unexpected responses during a maneuver, reduce the intensity of your inputs. The fifth one is the pilot must be aware of the sensitivity of the flight controls due to the high speed of the main rotor. Helicopter main rotor spin at high speed to generate lift. Last one is anticipate change in an aircraft performance due to loading or environmental conditions. Next slide, please. So here are more guidelines. When left turns and torque increases, when making a left turn, the torque or rotational force produced by the engine tend to increase. This is due to the interaction between the main rotors rotating and helicopter's fuselage. Second one is when right turn is firstly during this turn, the torque decreases and anti-torque effects is less pronounced. Application after cyclic. When you apply after cyclic, pulling a cyclic stick towards you, several things can happen. The torque decreases, it tends the helicopter to rotate around the vertical axis lessens. The rotor speed increases. So by adjusting the cyclic, you alter the blade pitch, affecting lift and rotor speed. Forward cyclic after cyclic. If you apply forward cyclic immediately after an after cyclic input, the torque increases, the helicopter's tendency to rotate around its vertical axis intensifies. Then a rotor speed decreases, adjusting the cyclic affects lift and rotor speed. Wind awareness, understanding the direction and strength. Wind affects helicopter stability and performance. You must adjust your flight path accordingly. Engine failures and carburetor icing. Ignoring carburetor air temperatures can lead to carburetor icing, which may lead or may cause engine failure. Crew coordination. An effective communication and coordination among crew members are critical. Steep turns and altitude management. A failure to anticipate this at low altitude can be dangerous. Landing coordination. Normal helicopter landings often require high power settings. Terminating a descent into a lower, for example, landing, demands a highest power setting. Last one is the cyclic position altitude. The cyclic position relative to the horizon directly influences the helicopter's travel direction and altitude. Mastering cyclic control is an essential for a precise maneuvering. Next slide, please. So there are 4 fundamentals upon which maneuvering are based. First one is straight and level flight. The fundamental skill involves maintaining a consistent altitude and heading. Second one is turns. Initiating turn involves using light touch on the aileron flight controls to bank the wings in a specific direction. Next slide, please. Third one is climb. Transitioning from a level flight to a climb requires an additional lift to overcome gravity. Increased power setting or thrusts are necessary to maintain a climb. The climb rate is limited by the potential for excess thrust. The fourth one, or the last one, is the transitioning from level flight to a descent. Lift is reduced, allowing excess thrust to produce higher airspeed. Next slide.
The first fundamentals of flight is the straight and level flight, in which the aircraft maintains a consistent heading and altitude. This maneuver is fundamental and constitutes a significant portion of typical flight operations. Straight and level flight familiarizes pilots with essential flight controls, pitch trim, and the fundamentals of controlling aircraft attitude. Next slide. When conducting straight and level flight, the pilot must utilize external and internal visual references. The natural horizon serves as a crucial reference for maintaining the helicopter's alignment. If the horizon appears to rise, it may indicate a need for slight power adjustment or a potential downward pitch of the helicopter's nose. Conversely, if the horizon appears to descend gradually, reducing power might be necessary as the helicopter's nose may be pitched too high, necessitating a cyclic adjustment. The, the cyclic, located at the pilot's right, functions as a control stick that influences the helicopter's flight direction by tilting the rotor disc in the desired direction. Then regarding the internal references, the primary instrument is the attitude indicator, which indirectly indicates the helicopter's pitch attitude during straight and level flight. Since maintaining a constant attitude is crucial for level flight, any deviation from the desired attitude signals a requirement for adjusting the pitch attitude and, if needed, power input. Next slide. Some common errors for straight and level flight are: first, the failure to trim the helicopter properly, tending to hold anti-torque pedal pressure and opposite cyclic. This is commonly called cross-controlling. The second one is the failure to maintain desired airspeed. The third one is the failure to hold proper control position to maintain desired ground track. And the last error is the failure to allow helicopter to stabilize at new airspeed. Next slide.
So next we have is the turns. What is a turn? A turn is a maneuver used to change the heading of the helicopter. There are two types of turns. First one is the turning while in hover. This is also known as a yaw. This is similar to being sat in a spinny chair, office chair, and someone rotates you round and round. This type of turn is accomplished by the tail rotor. The second one is turning while in flight. This is also known as roll. This is similar to learning on a bicycle when entering a fast turn. This type of turn is accomplished by the main rotor. So here are some techniques in turns. So before any turn, the area or vicinity in the direction of the turn must be clear. To turn from a straight and level flight, apply sideward pressure on the cyclic in the direction the turn is to be made. Do not use the pedals to assist the turn. Use the pedals only to compensate for torque to keep the helicopter in trim around the vertical axis. Keeping the fuselage in the correct streamlined position around the vertical axis facilitates the helicopter flying forward with the least drag. So the cyclic. So the purpose of the cyclic pitch control is to tilt the tip path plane in the direction that horizontal movement is desired. The thrust component of force then pulls the helicopter in the direction of rotor tilt. So to trim an aircraft, it is to adjust its aerodynamic forces on the control surfaces so that the aircraft maintains the set altitude without any control input. Now, the yaw string is also known as the slip string. It is a tool used to indicate slip or skid during the flight. It is simply a string attached to the nose or canopy of an aircraft so that it is visible to the pilot during flight. During a level coordinated turn, the rate of turn is commensurate or equivalent with the angle of bank used, and inertia, and the horizontal component of lift, which is also known as the HCL, and this all should be equal. Now, to determine the speed on the helicopter in terms of banking depends on the lateral cyclic pressure applied, and determining how far the banking may occur relies on how long the cyclic is displaced. After achieving the desired proper bank angle, the cyclic put the cyclic to neutral by holding it inclined relative to the horizon, thus maintaining the helicopter at the blade angle. So pictures below are the different types of controls used while turning. So as the torque increases, increase the power anti-torque pedal pressure to maintain the longitudinal trim. Depending on the degree of bank, additional forward cyclic pressure may be required to maintain airspeed. In terms of rolling out of the turn to straight and level flight, this is the same as the entry into turn, except that the pressure on the cyclic is applied in the opposite direction. Since the helicopter continues to turn as long as there is any bank, start the rollout before reaching the desired heading. So on-level turns are equally applicable to making turns while climbing or descending. This is also called as the simultaneous entry. It is where entering a turn while at the same time climbing or descending is desired, merely combining the techniques of both maneuvers with climb or descent entry and turn entry. When recovering from a climbing or descending turn, the desired heading and altitude are rarely reached at the same time. If the heading is reached first, stop the turn and maintain the climb or descent until reaching the desired altitude. On the other hand, it is the vice versa. If the altitude is reached first, establish the level flight attitude and continue the turn into the desired heading. Now, there are two types of uncoordinated terms. There are slips and skids. Now, the slip occurs when the helicopter slides sideways toward the center of the turn. This is caused by the insufficient amount of anti-torque pedal in the direction of the turn, or it is also caused by too much in the direction opposite of the turn. In relation to the power used, if you hold improper anti-torque pedal pressure, this keeps the nose from following the turn. The helicopter slips sideways towards the center of the turn. So in the terms of slips, the HCL is much more larger than the inertia. Next is the skids. So a skid occurs when the helicopter slides sideways away from the center of the turn. It is caused by too much anti-torque pedal pressure in the direction of the turn or by too little in the direction opposite the direction in relation to the amount of the power used. So an example is if the helicopter is forced to turn faster with increased pedal pressure instead of by increasing the degree of bank, it skids sideways away from the center of the turn instead of flying in its normal curved path. So in skids, the moment of inertia is much more greater compared to the HCL. So here are some techniques for the skid and slips. So if the pilot wishes to climb faster with a decreased airspeed, then the climb can be initiated with aft cyclic depending on initial or entry airspeed for the climb. However, as the airspeed decreases, the airflow over the vertical fin decreases, necessitating more anti-torque, which is the left pedal application. To level off from a climb, start adjusting the altitude to the level flight attitude a few feet prior to reaching the desired altitude. The amount of lead depends on the rate of climb and the time of level off. So to begin the level off, apply forward cyclic to adjust and maintain a level flight altitude, which can be slightly nose low, maintaining climb power until the airspeed approaches the desired cruising airspeed, then lower the collective to obtain cruising power and adjust the throttle to obtain the maintaining cruising RPM. So for the common errors, skids and slips. First one is failure to maintain proper and airspeed. Second is holding too much or too little anti-torque pedal. And the third one is in the level of decreasing power before adjusting the nose to cruising altitude.
Let's now discuss normal climb, which is the third fundamental flight. Since the entry into a climb from hover was described in another section of the FAA Chapter 9, I will only be discussing entry into a climb from cruising flight. I will discuss briefly the technique on how to enter climb. So the collective and throttle are increased and the pedals are adjusted as necessary in order to maintain a centered ball in the slip or skid indicator as shown in the picture to the left. Next slide, please. Remember that the climb attitude of a helicopter is approximately the same as level flight in a stable climb, since its attitude changes mainly indicates acceleration or deceleration, not climb or descent. Therefore, a helicopter can climb with its nose down and vice versa, or it descends with its nose up. If a pilot wishes to climb faster with a decreased airspeed, then the climb can be initiated with aft cyclic. However, as the airspeed decreases, the airflow over the vertical fin decreases, which necessitates more anti-torque pedal application. But the climb can be accomplished without an increase in the collective, if a much slower airspeed is acceptable, but it still depends on the airspeed when entering the climb. When leveling off from the climb, the attitude is adjusted to the level flight attitude a few feet prior the desired attitude. Generally, it is 10% of the lead of the climb rate. Remember that the higher the climb rate, the more the lead. So for example, if the climb rate is 500 feet per minute, the level off would be led by 10%, so 50 feet. When leveling off, forward cyclic is applied and level flight is maintained until the airspeed approaches the desired attitude. Then the collective is lowered to obtain cruising power and the throttle is adjusted to maintain cruising RPM. Throughout the level off, the longitudinal trim is maintained through the use of the anti-torque pedals. Next slide, please. So in normal climb, just like the previous maneuvers, there are common errors which are the following. First, failure to maintain proper power and airspeed. Second, holding too much or too little the anti-torque pedal, which simply means not applying the proper pressure. And the last, decreasing power before adjusting the nose to cruising altitude when in the level off. Next slide, please. So the next maneuver I will discuss is the normal descent. As shown in the presentation, it refers to the maneuver where the helicopter loses altitude at a controlled rate in a controlled attitude. Next slide, please. So the technique for normal descent is as follows. From a straight and level flight at cruising airspeed, normal descent is performed by lowering the collective to obtain proper power, adjusting the throttle to maintain the RPM, and increasing pressure on the right anti-torque pedal to maintain heading if in a counterclockwise rotor system, and the opposite, which is the left pedal if in a clockwise system. On the other hand, if cruising speed remains the same or slightly above the descent airspeed, necessary pressure to the cyclic is applied in order to achieve the descent attitude. A pilot should remember that the total lift and thrust is controlled by the cyclic. Therefore, if a certain airspeed is desired, the cyclic and collective movement is required in order to maintain a level flight. When leveling off from descent, the collective is increased, throttle is adjusted, and pressure on the left anti-torque pedal to maintain heading. Adjust the cyclic to obtain cruising airspeed and a level flight attitude as the desired altitude is reached. The desired altitude is led by 10% of the rate of descent. So like the example before in normal climb, if the rate of descent is 500 feet per minute, a 50-foot lead is required. Next slide, please. So the common errors for this maneuver include 1. Failure to maintain constant angle of descent during training. 2. Failure to level off the aircraft sufficiently, which results in recovery below the desired altitude. And the last, failure to adjust anti-torque pedal pressures for changes in power. Next slide, please.
Next slide, we have vertical takeoff to a hover. A vertical takeoff to a hover involves flying the helicopter from the ground vertically to a skid height of 2 to 3 feet while maintaining a constant heading. So here, once the desired skid height is achieved, the helicopter should remain nearly motionless over a reference point at a constant altitude and, and, and on a constant heading. The maneuver requires a high degree of concentration and coordination. Under technique, before performing a vertical takeoff to a hover, the pilot must clear the area and obtain clearance from controlling tower while focusing outside the aircraft. And if the pilot has a co-pilot who does not control the helicopter, he should assist in clearing the aircraft and provide an adequate warning of any obstacles and any unannounced or unusual drift or altitude changes. And as a review, pedals controls the heading, direction of turn, and rate of turn. Collective controls the hover height, rate of ascent, and descent. And the cyclic controls the helicopter position and direction of travel. Um, in vertical takeoff to a hover, it should begin, the pilot should begin to maneuver the collective in the down position and the cyclic in the neutral position or slightly into the wind. Then very slowly increase the collective until the helicopter becomes light on the skids or wheels. During the maneuver, the pilot gradually increases collective while adjusting anti-torque pedals, maintaining heading and coordinating cyclic for ascent, ensuring proper altitude control response and center of gravity, while adjusting flight controls to maintain hover position and noting engine instrument for power required. And another thing, excessive movement of any flight controls also require a change in other flight controls. For example, if the helicopter drifts to one side while hovering, the pilot naturally moves the cyclic in the opposite direction. However, this can easily lead to over-controlling the helicopter. And that is why piloting helicopters is associated with such a high level of proficiency. Next slide, we have the common errors. Number one, failing to ascend vertically as the helicopter becomes airborne. Number two, pulling excessive collective to become airborne. This caused the helicopter to gain too much altitude. Third is over-controlling and anti-torque pedals, which not only changes the heading of the helicopter, but it also changes the RPM. Fourth, we have reducing throttle rapidly in situations in which proper RPM has been exceeded. Usually, this results in exaggerated heading changes and loss of lift, resulting in loss of altitude. And lastly, failing to ascend slowly. Next part, we have hovering. A hovering or a stationary hover is a maneuver in which the helicopter is maintained in nearly motionless flight over a reference point at a constant altitude and on a constant heading. Technique. Maintaining a hover over a point in the helicopter requires utilizing side view and peripheral vision to detect small changes in attitude and altitude, making necessary control inputs preemptively. Attention should be focused at a distance from the aircraft to detect subtle variations in positions without over-controlling. And a tip, to maintain the helicopter in a stabilized hover, the pilot should make small, smooth, and coordinated corrections. As the desired effect occurs, the pilot should remove the correction in order to stop the helicopter's movement. For example, if the helicopter begins to move rearward, they should apply small amount of forward cyclic pressure. Through practice, pilots develop what you call a certain feel or a intuitive sense of the helicopter's behavior, allowing for smooth, coordinated corrections to maintain a stabilized hover as controlling becomes their second nature. And based on their flying experience, small deviations can be felt and seen by pilots, so they can make the corrections even before the helicopter actually moves. Next slide. The common errors, number one, tenseness and slow reaction to movement of the helicopter. Number two, failure to allow for lag in cyclic and collective pitch, which leads to over-controlling. It is very common for students to, for helicopter pilot students to get ahead of the helicopter. Due to inertia, it requires some small time period for the helicopter to respond. Third, confusing attitude changes for altitude changes, which results in improper use of the controls. Fourth, hovering too high, creating a hazardous flight condition. The height velocity chart, which will be discussed by Mr. Molenio later on this report, should be referenced to determine the maximum skid height to hover and safely recover the helicopter should a malfunction occur. Fifth, hovering too low, resulting in occasional touchdown. And lastly, number six, becoming overly confident over prepared surfaces when taking off to a hover. They should be aware that dynamic rollover accidents usually occur over a level flight.
Next is the hovering turn. A hovering turn is a maneuver performed at hovering altitude in which the nose of the helicopter is rotated left or right while maintaining position over a reference point on the surface. This maneuver requires the coordination of all flight controls and demands precision control near the surface. During a hovering turn, use cyclic and pedal controls to maintain position over a spot, adjusting pressure as needed to counter crosswind forces and control altitude. Anticipate changes in control requirements, particularly as the helicopter transitions through different wind conditions. Consider rotor system configuration when choosing the turn direction and avoid performing hovering turns in strong winds that may affect control. Next slide. To perform a hovering turn, let's refer to this picture. It shows a left turn in the helicopter. So we'll start from left to right. So the first position, while the helicopter remained in a hover, ground visual references were utilized, resulting in the application of a slight pressure on the left pedal, indicate initiating a leftward turn on the helicopter. The second position, we add more left pedal pressure as the helicopter turns to the crosswind position. During the turn, do not forget to use the cyclic if the helicopter begins to lean to the left and thus to move horizontally. The third position is where after the 90 degrees part of the turn, we apply less pressure on the left pedal and continue to turn in a constant rate until reaching 180 degrees of the turn, and keeping ready to apply the right pedal pressure in case of need due to the helicopter's tendency to weather vane positions 3 and 5. The fourth position is the continuation of the left turn at a constant rate during hover depends on factors such as wind conditions and the type of helicopter being used. This may require adjusting the pedals accordingly. Sometimes, using the right pedal to counteract the helicopter's tendency to weather vane, sometimes maintaining slight pressure on the left pedal, and occasionally keeping the pedals in the neutral position. Regardless of the specific adjustment needed, the primary objective remains to sustain the turn at a consistent rate while maintaining hover stability. And the last position is where the left turn is terminated. The helicopter is about to complete a 360 degrees turn, and we apply a pressure on the right anti-torque pedal to stop the turn. Next slide. Some common errors when performing a hovering turn includes the following: failing to maintain a slow constant rate of turn. The next one is failing to maintain position over the next reference point. Next is failing to maintain RPM within normal range. The fourth one is failing to maintain constant altitude. And the last common error for hovering turn is the failing to use anti-torque pedals properly. Next slide.
So next is the hovering forward. It is normally used to move a helicopter to a specific location, and it may begin from a stationary hover. During the maneuver, constant ground speed, alti- altitude, and heading should be maintained. So these are maintained by the cyclic, collective, and anti-torque pedals respectively. So what is the technique to do the hovering forward? First is to pick two reference points. This would tell the pilot whether he or she is moving in a straight line while moving forward. After picking a reference point, forward pressure is applied on the cyclic while moving, it is slowly returned into neutral. This is to prevent the helicopter to move too much forward. So in order to stop the forward motion, the pilot could just apply rearward cyclic pressure until the helicopter stops and return it to neutral. So forward movement can also be stopped by simply applying rearward pressure to level the helicopter and allowing it to drift to a stop. Next slide. So next is the hovering sideward. Sideward hovering flight may be necessary to move the helicopter to a specific area when conditions make it impossible to use forward flight. During the maneuver, constant ground speed, altitude, and heading should be maintained. So what is the technique to do the sideward hovering? So the technique to do this is to first ensure that the area is clear. So next is to pick two reference points which would be a guide for the pilot. A sideward cyclic pressure is then applied to where you want to go. So as the movement begins, slowly return the cyclic toward the neutral, and in order to stop the sideward movement, the pilot could apply pressure to the other side and then slowly bring it back to neutral. So next slide, please. So last is the hovering rearward. This may be necessary to uh to when forward and sideward hovering flight cannot be used. During the maneuver, constant ground speed, altitude, heading, tail rotor clearance, and RPM should be maintained. Generally, a higher than normal hover altitude and the use of ground personnel is recommended. So the technique used to apply to do this hovering rearward is just like for the forward hovering but in the opposite direction. So the technique is first to ensure the area is clear. Second is to pick two reference points directly in front and in line with the helicopter. Then apply rearward pressure on the cyclic, and as the movement begins, slowly return the cyclic toward the neutral position. To stop the rearward movement, apply forward cyclic pressure until the helicopter stops. Next slide. So these are the common errors for the three hovering flights. So first is exaggerated movement of the cyclic, resulting in erratic movement over the surface. Second is failure to use proper anti-torque pedal control, resulting in excessive heading change. Third is failure to maintain desired hovering height. Fourth is failure to maintain proper RPM. And lastly, failure to maintain alignment with direction of travel. Next slide.
So next we have is taxiing. So taxiing refers to operations on or near the surface of taxiways or other prescribed routes. Helicopters utilizes three different types of taxiing. We have hover, air, and surface taxiing. So for the hover taxiing, it is used when operating below 25 feet above ground level, as shown in the figure below. Since hover taxi is just like forward, sideward, or rearward hovering flight, the technique to perform it is not presented here. Next is air taxi. Air taxi is preferred when movements require greater distances within an airport or heliport boundary. In this case, fly to the new location. However, it is expected that the helicopter will remain below 100 feet with an appropriate airspeed and will avoid overflight of other aircraft, vehicles, and personnel. So techniques for hover and air taxi: determine the appropriate airspeed and altitude combination to remain out of the cross-hatched or shaded areas of the height velocity diagram. So what is the height velocity diagram? So this diagram shows the combinations of airspeed and height above the ground, which allow an average pilot to successfully complete a landing after an engine failure. By carefully studying the height and velocity diagram, a pilot is able to avoid the combinations of altitude and airspeed that may not allow sufficient time or altitude to enter a stabilized authoritative descent. Next is be aware of crosswind conditions that could lead to loss of tail rotor effectiveness. So pick out two references directly in front of the helicopter for the ground path desired. This reference point should be kept in line throughout the maneuver. Next is begin the maneuver from a normal hovering height by applying forward pressure on the cyclic. As movement begins, attain the desired airspeed with the cyclic, control the desired altitude with the collective, and RPM with the throttle. Next is maintain a desired ground speed and ground track with the cyclic. A constant heading with anti-torque pedals, the desired altitude with the collective, and proper operating RPM with the throttle. Next is to stop the forward movement aft. Apply aft cyclic pressure to reduce forward speed. So simultaneously lower the collective to initiate a descent to hover altitude. As forward motion stops, return to the cyclic to the neutral position to prevent rearward movement. And lastly, as approaching the proper hover altitude, increase the collective as necessary to stop descent at hover altitude. Next are the common errors for the hover and air taxi. The first one is erratic movement of cyclic, resulting in improper airspeed control and erratic movement over the surface. Second is failure to use proper and anti-torque pedal control, resulting in excessive heading change. Third is failure to maintain desired altitude. Fourth is failure to maintain proper RPM. Fifth is overflying parked aircraft, causing possible damage for rotor downwash. Sixth is flying in the crosshatched or shaded area of the height velocity diagram. Seventh is flying in a crosswind that could lead to loss of tail rotor effectiveness. Eight is excessive tail low altitudes. Nine is excessive power used or required to stop. And the last one is failure to maintain alignment with direction of travel. Next we have is surface taxi. So surface taxi is used to minimize the effects of rotor downwash in wheel type helicopters. Seen in the figure below, surface taxi in skid type helicopters is generally not recommended due to the high risk of dynamic rollover. So the techniques used in surface taxi, the helicopter should be in stationary position on the surface with the collective full down and the RPM the same as used for a hover. Next is use the anti-torque pedals to maintain heading and the cyclic to maintain ground track. Third one is the collective controls should be applied in starting, stopping, and speed while taxiing. And the last one is during a crosswind taxi, hold the cyclic into the wind a sufficient amount to eliminate any drifting movements. So for the common errors for the surface taxi, we have the first one is the improper use of the cyclic. Second is failure to use anti-torque pedals for heading control, which causes an imbalance to the helicopter. Third is improper use of the control using crosswind operations. And fourth is to maintain proper failure to maintain proper RPM. So that concludes our presentation. Thank you for listening.